Today we're looking at graphs, and we're doing it in two different ways between this lesson and the next. One is what we call a point plotting method. That's in today's section. And then in the following section we have graphing by transformations. But we're overviewing both of those here first by looking at the parent functions. And so I went ahead and filled this in just to kind of speed up on the recording time here. These are the basic parent functions that we have worked with over the past couple of math years. So in Algebra 1, you mainly focus on maybe linear and quadratic and absolute value, for example, and then maybe in Algebra 2 you add in a few more. So what we're looking at here are these critical values, these key points. You can see that we have 5 inputs, and we get the output simply by taking inputs and plugging them in. And then when you plot those points, that gives you the shape of the graph. So you want to memorize the shape of the graph so that when you see an x cubed in an equation, you know that would be its overall shape when you graph it. When you see square root of x in an equation, you know that if we were to graph it, that would be its shape. So you want to memorize the shape, and you want to memorize the kinds of inputs that we're selecting here, because while the first 4 use the same 5 inputs, the next 2 don't. The square root, we're using 0, 1, 4, 9 as inputs because we cannot plug in a negative value and get a real answer. And we want to be able to do this by hand. We want to plug in a number that is a perfect square so that we can figure this out without a calculator. Square root of 4 is 2, for example. That's why we're skipping over an input of 2 or an input of 3. And then for the cubed root, again, we want to select values that are perfect cubes so that we can take the cubed root of 8 and know it gets us an answer of 2 without needing a calculator to get a decimal value. We'll be looking at these shapes for both the point plotting method as well as the graphing by transformations method. So I'll give you a chance to copy this down, and then we'll go to the next page and look at some more introductory materials. Here on the next page is a summary of the two methods. You can see here we have the point plotting method. That's what we'll see an example of in today's lesson. And then in the next lesson, this is the transformation method. And I want to spend some time talking about it here just because you can see I've filled in some stuff ahead of time already. So this is going to be the general pattern of identifying where we will find values of A and B, H and K, and then how they will affect the shape and placement of the graph. When we go through this method, we want to identify the parent function, meaning is it an x squared, is it an x cubed? So you would look for the exponent, and right here there's no exponent. And that's because we're really just focusing on where you would find it, the A, the B, the H, and the K. But if you had absolute value, you would have the absolute value signs. If you had an x squared, you would have a power of 2 right there. If you had a square root, you would have a square root symbol. So the symbol itself will change depending on whatever equation we have. So we're going to find the parent function, we'll make a table, and then we'll check for reflection, stretch, and translate in that order. If you do translate first and reflection last, it just won't work out. So I'm going to walk you through the steps, but this method is actually what we're going to see on the next lesson. Then we'll come back and talk about this method number 1 because we'll see an example here in just a moment taking you through that. So what you're looking at here is the value of A really does two things. If it's a negative sign, it'll give us a reflection. And then the value itself, not looking at the negative sign, but looking at the value, if the value is bigger than 1 or less than 1, it will also change the height. So what you're looking at here is the reflection. We can reflect over the x-axis if we have a negative sign outside of the grouping symbols where we have the letter A represented. We will see a reflection over the y-axis if we have a negative B. Notice this is inside the grouping symbols. So the reason why we say x is positive is because if you happen to see a negative with the x, you want to treat it as if the negative sign were located here, if it happens to be inside the grouping symbols, or here if it's outside of the grouping symbols, and that way it forces the x to be positive. If the value of A is greater than 1, that means it's being stretched taller. It will be 2 times taller or 3 times taller, depending on what that number is. If, however, the value of a is less than 1, like 1/2, well, then we'll see it shrink in its height, so it'll be half of the size. But not negative, because negative is covered over here in the reflection. So we say between 0 and 1 will give us a shrink. Then we're looking at the h and the k. We're starting off with the k over here. If you see a positive k, that means we're shifting or translating up that many units. And if you see a negative k, that means you're going to go down. But it's reversed for the h. If you see a negative h, you actually have to think the opposite. That does not mean left, it means shifting to the right. And if you see a positive h right here, that does not mean right. You have to think in the opposite direction. You're going to shift it to the left. Notice also I scratched out the horizontal stretch. We're really just focusing on the vertical stretch here. So let's take a look at example number 1, which is down here, and that's going to talk about this point plotting method. So here are the steps that you can see it kind of detailing what's going on here. Rewrite the equation. So one of the variables is isolated, meaning solve for y. Then we'll make a table of several solution points. We'll plot those points. We'll connect those points with a smooth curve. All right? So again, I've already filled this out just to kind of save time on the recording. When we do the point plotting, let me suggest you pick 5 inputs. So here are my 5 inputs, -2, -1, 0, 1, 2. So notice we're not using our graphing calculator, of course. That is another method altogether. But for the point plotting method, you just pick 5 individual points, discrete points. You plug them in for x, one at a time. You then simplify. So we have a root 3, a root 2, a root 1, a root 0, and a root -1. And because we're plotting, we want to know where to put them. So here is the decimal value so we can figure out where they go. So those are my outputs. Now I know the graphing calculator can of course generate that table for you, but the concept is that you can do this by hand without a calculator simply by putting an input, plugging it in, and then seeing what the output is, and then graphing the results. And in this particular case, we have an undefined result, so we cannot graph anything with an input of 2. So that's why you don't see that represented on the graph. That is our termination point on the square root function. And with the minus sign being inside the grouping symbols, what we see is a reflection from right side to left side. So instead of going to the right, we're now going to the left. So we'll get more into that when we're graphing by transformations. Let me turn the page and continue on with a couple more topics here. Talking about a solution point. A solution point is an ordered pair that satisfies the function, satisfies the equation, and that means the point is on the graph of that function. So without actually graphing it, without actually plotting the points, let's determine if the point lies on the graph, meaning does the point satisfy the function, satisfy the equation. So again, I filled this out ahead of time just to save on some recording time. So here's your input, here's your output, meaning this is your x coordinate, this is your y coordinate. So in place of x, substitute in a 0. In place of y, substitute in a 0 for this equation where it says y equals 1 over the quantity x squared plus 1. So what you're seeing here is I plugged in my y coordinate of 0 on the left-hand side. I plugged in my x coordinate, which is also 0 here in place of x. And we're really asking the question, is this a true statement? And when we simplify the right-hand side, we find the right side equals 1. So that means it does not equal 0. So that means this point does not lie on the line. This ordered pair, this coordinate point, does not satisfy the function. Here's another example. Here's your x coordinate of 3. Here's your y coordinate of 0.1, 1/10. And so in place of y, I'm substituting in the 0.1. That's what you see on the left. And in place of x, substituting in the 3 on the right-hand side. And then we simplify. We get 1 over 3 squared, which is 9. 9 plus 1 is 10. So 1/10 is the same as 0.1. So yeah, that checks out. So that means if we were to graph the function and plot the point will be found to lie on the line. So that means it is a solution point. It does satisfy the function. We also have something called intercepts, so we'll work this through together here. We could have an x-intercept or a y-intercept. So this is the key piece right here. If it's an x-intercept, that means it is on the x-axis. That means we will have an ordered pair where we'll have a number for x, but the y is 0 because you're not above the x-axis, you're not below the x-axis, you're on the x-axis, so that has to be 0. To find that x-intercept, let y equal 0 and then solve for x. However, if you're talking about a y-intercept, that means you know a value for the y-coordinate, but now your x is set to 0 because you're not to the right, you're not to the left of the y-axis, you're on the y-axis. And again, to find that y, you have to set x equal to 0. Why? Because there it is, x has to be 0. So let's do that for these examples. Here's example 3. We have x equals y squared minus 3. So if I want to find the x, that's what we're doing right here. I want to find the x-intercept. That means my y-coordinate has to be 0. So set y equal to 0. So I have x on the left equals y squared. Plug in a 0. 0 squared minus 3. We're going to solve for x, and we get an answer of negative 3. Now write your answer as an ordered pair, because what we're saying is when x is negative 3, y is 0. Let's now find the y-intercept. So to find y, that's this one. To find y, that means the x is set to 0. Set x equal to 0. So here we have 0 on the left-hand side because that's where x is. That equals y squared minus 3. Our goal is to solve for y. So let's add 3 to both sides. And then we'll take the square root of both sides. And remember your plus or minus when you take the square root of that. That means you have 2 y-intercepts. So that means you have 0 comma root 3 as well as 0 comma negative root 3. Let's do one more. Here's part B. In this one, we have y equals x cubed minus 4x. So let's start by finding the x-intercept. That means set the y to 0. So to find x, I will set y to 0. So I'm plugging in 0 on the left-hand side. 0 equals x cubed minus 4x. Now you have to think, okay, how do we solve that? Remember, factoring is going to help us out a lot as we have a common factor of x. So 0 equals x times x squared minus 4. And now we have a difference of perfect squares. So that'll factor into x plus 2 and x minus 2. Every factor is being multiplied together. And we have something called the zero product property, which means we have a 0, we have a product. Product is multiplication. And the property says that you can set every factor equal to that 0. And then solve each of these factors individually. So x equals 0, we got that one. X equals negative 2, and then x equals positive 2. So we actually have 3 x-intercepts. 0 comma 0, negative 2 comma 0, and positive 2 comma 0. Lastly, for the y-intercept, if I want to find the y-intercept, I'm going to find the y. That means we want to set x equal to 0. So we have y equals, here's my substitution of 0 in for x, so 0 cubed minus 4 times 0, which is just 0. So what we have here is a y-intercept at the origin, and that's why it matches this x-intercept, which is also at the origin. So those agree with each other. Here's the last topic we're looking at, looking more with the equations of circles. We had done circles in the previous lesson, and what we're going to do here is reformat this in such a way so that we could type this into our graphing calculator, and then we'll sketch what we're seeing on our calculator. So if we want to type it into our calculator, that means we want to use the equation editor, and that is always set up as y equals the rest of your equation. That means we have to get y by itself. So if I want to graph this circle on my calculator, what that is really saying is I need to manipulate the equation and solve for y. We want to isolate the variable y. So to do that, what we need to do is figure out where the y is. Okay, that's easy enough. And we go to the other expression first. We're going to move this binomial to the other side. So let's subtract the whole bundle and move it to the other side. So what that means is now we have on the left-hand side the y minus 2 squared, and on the right-hand side you have your 16, and because we moved this bundle to the other side, we're subtracting it from both sides, so it's minus the entire binomial. Okay, so don't distribute the negative sign. Don't FOIL out the binomial, just leave it in that format. Next, we're going to take the square root of both sides to get rid of this power of 2. Again, our goal is to get y by itself, so we have to get rid of this power of 2, and we have to get rid of this minus 2. So let's take the square root of both sides, and when we do that, remember that you get a plus and minus. There's always two answers. So you have y minus 2 on the left, because the square and the square root cancel out. On the right-hand side, you have your plus or minus square root of 16 minus that bundle, that binomial, x minus 1 quantity squared. Now just pause for a moment. Think about this. Can I take a square root of this 16 right here? Can I take the square root of this power of 2? Will they cancel out? You might be tempted to, but don't. Do not do that. And the reason is because the radical is a special kind of grouping symbol. What that means is you cannot take a square root of individual terms, like the 16. You can only take the square root of the whole thing. Let me illustrate that a little bit further. Back in the previous unit, we learned this property. If you are multiplying, that means if you have factors, if you are multiplying things, then you can take the square root of individual factors, but that only works for multiplication. If you have an addition sign or a subtraction sign, can you split up your radicals this way and take the square root of only the a and only the b? No. This has to be grouped together as a bundle. So what that means is if you're multiplying, then you can take the square root of each individual base, each individual factor. But if you have addition or subtraction, you cannot take the square root of 16 because 16 is not a factor, 16 is a term. So it stays this way, in other words. As we add 2 to both sides, I'm going to write this in a slightly different way because, again, our goal is to be able to type it in our calculator, and I can't type in a plus or minus at the same time. So I'm going to type in a positive version of the radical, and then I'm going to type in a negative version of the radical. So in our calculator, you have a y sub 1 and a y sub 2. Those are what we need to type in. And so I'm going to do that here in just a moment and show you what I've got. All right, so I typed those in, and you can see those are the equations there. It takes a while to make sure you get all of the grouping symbols in the right place. There's your plus radical, there's your minus radical. And for the x, you have an input variable right here. It's next to the alpha key. So that's how I'm getting the x. And then once we type that in and we go to the graph, that's what it looks like. So you can see that there's a top half that's clearly separated from the top half. It looks like there's a break right there. And that's because these cannot graph vertical lines. So as we get closer to the vertical line on the left-hand side, it just can't close the gap. There's a very tiny gap on the right-hand side. I don't know if you can see that from where you are. Also, it's kind of squashed, and that's because it's wider than taller on this rectangular screen. So to fix that, and that's what this box is about, go to your zoom settings, so right here in the middle, and you'll see option 5, which is zoom square. And so selecting that one, it then adjusts the width and the height, so now you have something that looks more like a circle. Notice you still have those gaps on the right-hand side. So what we're doing here is we're actually sketching what we see. So we're not drawing an ideal circle, we're drawing what we actually see here. So we have this center. All right, we know this is our center. This is the H and this is the K, so we can confirm that the center is at positive 1 and positive 2. We know the 16 represents the radius squared. So we know the radius is 4. So just using those as my guide points. However, to graph what I'm seeing that empty break on the left and the right side. So I want to represent that here as well. So I'm going to not go all the way down to those points. I'm going to kind of start up here and separate the top half from the bottom half, something like this. So that's what I'm seeing. Technically, I'm not seeing the dot on my graph on the calculator, but I put that there just so that I could graph the radius.